Today's episode is proudly sponsored by Radical Polymers. Nation, running a water treatment business is hard. Dealing with your suppliers shouldn't be. And when I deal with the fine folks over at Radical Polymers, I have always felt like I have had a partner. They test things in the environment that we are going to use their products. They also make sure that if I have any questions, that I get the answer that I am looking for. Mike and the fine folks over at Radical Polymers answer the phones. Folks, when was the last time you actually talked with somebody when you had a technical support question? Well, they make your issues their issues and they get right down to the problem. They offer best-in-class technologies with the first-class support that I just mentioned. Go to scalinguph2o.com/radical to find out more. Welcome to Scaling Up, the podcast where we're scaling up on knowledge so we don't scale up our systems. Scaling Up Nation, my name is Trace Blackmore, and I am honored to be the host of Scaling Up H2O. And there is just so much going on. Of course, you all know, because I talk about it all the time, I am involved with the Association of Water Technologies. And next week, I will be in Cleveland, Ohio, doing the conclusion, not that it's a continuation series, but the second part of the training that we do. We normally do one training on the west side of the country, and then we do one on the east-ish side of the country. This time we're in Cleveland, Ohio. So I always love these trainings. I've been a trainer for AWT for, I don't even know how many years. It's been a while. And people always ask me, Trace, why are you giving away things that make you marketably more competitive than other water treaters? Well, of course, you out there in the Scaling Up Nation can answer that question. You know, a rising tide raises all boats. But here's the other thing that's going on there that I don't think everybody realizes. The more you give to this industry, the more that you will get back. So although I am giving things that I've learned over costly mistakes that I've made, and also things that I've created that didn't exist before I created them, there's several equations that I share with the audience. I do that knowing that that rising tide will raise all boats, but when I do that, people give back to me. They ask me questions, and through those questions, I get better insight. And I also get a network of people that I can call when I need help with an issue, because no one person knows everything. So when you can get a group of people that you can talk through situations around you, it is just amazing what happens from that. And that's really the basis of why I started the mastermind as well. But I want everybody to think about what are they doing so they're actually creating a community where they can get their questions solved. So I talk on this show quite a bit about what can you do to make yourself better? How do you get out of the day-to-day whirlwind that we are always in? But today I want you to focus on what are some things that you can do to make sure that you have a community of people so you can bounce questions off of. Again, when you can let people know what issues you are having, they can use their experience, maybe not to answer your question, but to ask questions in a different way that will allow you to solve them. And again, that is exactly what we're doing in the Rising Tide Mastermind, but there's so many other areas in life that you can use that same philosophy to get that same benefit as well. You know, I want to say I had a great time in Seattle, Washington a few weeks ago. So many people came up to me and gave me some great show ideas. I got some criticisms too, and folks, I don't mind those. Anything that you are going to share with me, makes me better. It makes this show better. And I think as the show gets better, we are going to make the industry better together. So thank you so much for those people that came up to me and gave me some advice. For all those that gave me some new topics and people to interview, I would not have a show without you. So I am hoping that I will receive that next week in Cleveland when I'm at the AWT training again. So if you've got something out there, don't keep that locked up inside your head. I've got so many ways that you can share that with me. I know you've heard people on the air ask questions and then I answer them. Those have been some of my favorite shows to do because I know I'm answering the questions that you want me to talk about. So if you have a question, you can go to our website, Scaling Up H2O, and you can go to our show comments page and you can leave a message there, or there will be a box on the right side of the screen that says leave voicemail, and you can record your own voice asking your question. Most likely, I'll play it on the air, and then I will answer your question. So thank you in advance for keeping those coming. Well, over the past few weeks, when I've been doing pinks and blues, you might have noticed that they've been a little themed. And I thought about this theme, but I didn't announce it. But I figure since we're 3 deep into it now, I will announce it. People have asked me to start doing math on the podcast. This isn't new. This has been years that people have been asking me to do this. And I just did not think it would be received well. Well, it turns out it's being received very well. And I've been getting some great comments coming back to me, people thanking me for explaining why we do some of the things we do when it comes to our math equations. So I figured let's continue that series. And we're in a series of rules of thumb. And for those of you that have been to any of my classes where we're talking about mathematics, and by the way, that's what I do with the training. I teach the mathematics portion, and people hate math, but I got to tell you, I love math for the simple reason it's the only thing you can really count on in water treatment. Everything else is so dynamic, it changes so much. And I know people will argue that math is only going to get you close, but I can't think of anything else that is as consistently close that will allow you to start a program and do it better than any other way than using the equations that we have in the water treatment industry. So with that, I have been pretty much my entire life looking for all the rules of thumb that we have and figuring out where they came from. Now, when I say rules of thumb, I'm specifically talking about the constants that are in our equations. If you ask a seasoned water treater, what is that constant number that's in the equation, they're going to say, hey, that's a rule of thumb. And what does that mean? Well, it probably means they don't know where it came from. But I would say that no one ever told it to them, and they just took it for face value that it is what it is. And for a lot of people, that is fine. However, for myself and how I learn and how I apply these equations, I need to know where something is derived from in order for me to truly understand what the equation is. And it's important for me to understand the equation because when I understand something, I can use it properly. And more important, when I use the equation, I can see whether the equation is giving me the correct data or not. If I don't know all the inputs that are going into that equation and understand why, the output is going to be totally oblivious to me, and I don't know if it looks like a right answer or not. So if you need a reason to start understanding some of the water treatment equations that we use better, then I would suggest you use that as your reason. Well, today I thought we would talk about why we use tonnage, and specifically, we have a rule of thumb that's tonnage times 3. And if you're looking for recirculation rates, those are typically tonnage times 3. And if you ask somebody, well, why is that? They'll say, oh, well, that's a water treatment rule of thumb. So what I want to do is go through where that actually comes from and see if we can all truly understand why it is tonnage times 3. So I want to start out with evaporation rate. Now, there's several evaporation rate formulas out there, but I think the most common one that we use is evaporation equals 0.001, so 1/1000th, times the recirculation rate times the delta T, that's the water in, water out temperature, and then times some sort of factor. So let's look at that equation really quick. So let's start with the 0.001. So that is a constant. Where the heck does that come from? Well, it takes 1,000 BTUs to evaporate 1 pound of water, and that number allows us to put that fact into the equation. Then we have our recirculation rate. So how fast is the water, gallons per minute, going through the system? Then we take the delta T, so the hot water coming in minus whatever temperature is lost and the cooler water going out. So if it's a 10-degree difference, say it's 90 degrees going in, 80 degrees going out, so that would be a 10-degree delta T. And then it's times a factor. So we don't get 100% evaporation when we put water through a system. So we have to equate for the sensible loss of heat. So depending on what region you are in, if we're talking about a cooling tower, you might use something like a 0.8 or you might use something like a 0.9. You'll have to reference that to see what your area is in. And then you would just simply use that number as the factor. So again, the equation, evaporation rate equals the 0.001. We know that it takes 1,000 BTUs to evaporate 1 pound of water times our recirculation rate. We don't quite know that yet if it's not listed, times our delta T, our change of temperature, times our factor, and that will give us our evaporation rate. Well, the other thing I want to look into is the recirculation rate. And the recirculation rate, if you were to ask somebody how to find that, and they would say, well, you got to add up all your pump GPMs, but I want to tell you, those are really, really difficult to find. And now we've got variable frequency drives on them. There's just so many different variables on there. It's not how most water treaters find recirculation rate. So you're going to ask somebody and they're going to say, oh, well, you just take the tonnage and you multiply that times 3, and that gives you the recirculation rate. And most of us have heard that, and we've done that for years, and we've never thought twice about it. Well, that's what today's show is going to do. We are going to talk about why we use tonnage times 3. But the first thing I would like to do is talk about why we use the word ton. And what does ton mean? Well, it all goes back to the fact that we are melting ice when we're trying to cool something, or more important, remove heat. So we're basically talking about a ton of ice. And all the equations that we are dealing with in this manner are focused around a ton of ice. Well, we have this big fancy term called the latent heat of fusion of ice. Now, what the heck does that mean? Well, I'm sure you know this, but I'm going to go into it anyway. If I have a glass of water and I have ice in the water and then I have liquid water, it's 32 degrees. So how does the ice know to stay ice and the water know to stay water? It's fairly interesting. Some of us might not have thought about that before, but what that is, that's the latent heat of fusion of ice. So here's the thing. We have to put energy into it. Specifically, we have to put BTUs, British thermal units, into the ice so it will phase change into water. Remember, water has 3 phases. We have solid, which is ice, liquid, which is water, and then gas, which is our steam. So we're now at the ice stage, And we have essentially, if you will, 32 BTUs in the ice because the ice is 32 degrees. But again, the water also is 32 degrees. So now when we look at the latent heat of fusion of ice, we have to add an additional 144 BTUs to convert that solid ice into liquid water. And now we have 32 degrees water. Pretty sure you've heard something like that before, but I'm surprised at how many water treaters don't realize that. Our job is BTU efficiency management. And folks, if you don't understand BTUs, it might be a good job, a good time for you to review that. So why don't we just do that now? So now we have water in its liquid form at 32 degrees. So water boils at 212 degrees. So that means we can add heat to the water, basically 180 BTUs worth. So we have 180 times, which is not the best way to say that, but we have this long span that we can add heat to water before its next phase change. Now, what that means is we have this broad spectrum that we can add heat. And the other cool thing about water is water does not get as hot as other substances do when you add heat to it. Now, in another series, I might prove that, but just take my word for it for this. Or if you come to the training next week, I promise I will talk about that. So with that, water is the best heat transfer medium out there for two reasons. One, it does not get as hot as other things when you add heat to it. And we have so much opportunity to add heat to it because it doesn't boil into 212 degrees. So now we're up to that 212 degrees and we have to convert it to steam. Well, it takes an additional 970 BTUs to convert that 212 degree water to steam. So steam, once we get it, has 1,150 BTUs in it. I'll do another episode. That's the reason we had the Industrial Revolution, but that's not the point of this one. And by the way, that 0.001 in the equation that I mentioned earlier, that's where that came from, that 970 BTUs. Well, water treaters are simple folk. I've said that several times. So we just round that up to 1,000. So that's where it takes 1,000 BTUs to evaporate a pound of water. Well, it really takes 970, but we're going to make it easy to remember, so we'll say 1,000. So is everybody with me there? There's a little brief comment on how the BTUs go with water. But now we got to get back to why we're using a ton. Now that we know that the latent heat of fusion of ice is 144 BTUs, we're going to put that knowledge into the equation. Again, that 144 BTUs is how many BTUs it takes for that ice to become water. So a ton is 2,000 pounds. So if we take 2,000 pounds and multiply that by 144 BTUs divided by our 24 hours, we get 12,000 BTUs per ton of water an hour. So that just told us a chiller ton removes 12,000 BTUs per hour. Now that still doesn't tell us where that tonnage times 3 comes from, but it does get us a little bit closer. So here's what we know. A chiller removes 12,000 BTUs per hour per ton. We just proved that. But a tower is sized to not only remove the BTUs that the chiller is taking out, because we got to get rid of it somewhere, that's what the cooling tower does, we also have to realize that the chiller is producing heat in the process of removing that heat. So we're going to add an additional 3,000 BTUs as parasitic heat from the chiller. So a tower ton is 15,000 BTUs per hour. Make sense? Chiller ton is 12,000 BTUs per hour, and a tower takes out not only the heat from the chiller that it's removed, but the parasitic heat that it puts into the system, which is an additional 3,000 for a total of 15,000 BTUs per hour. So how do we get to tonnage times 3? Here it comes. We know that water weighs 8.345 pounds per gallon. Now, flow rate is in minutes, but if you noticed, all the tonnage I talked about was all per hour. So we have to do a conversion there. So we have to convert our pounds per hour. So our 8.345 pounds times 60 to get it into an hour, we get 500.7. With me so far? So our flow rate and pounds per hour is our pounds of water, our 8.345, times 60 to get it into an hour. That equals 500.7. And then we know that towers are typically designed for the 10-degree removal of heat, a 10-degree delta T, if you will. So our 5,000.7 times 10 equals 5,007. So now let's put the two things that we just learned. We know that a tower ton is 15,000 BTUs. We learned our flow rate using pounds per hour based on the tower design is 5,007. So if we divide 15,000 by 5,007, we get roughly 3. And that's how we just proved tonnage times 3. So the next time you cannot find the GPM plate on the pump, and I don't know why, but it's never going to be there, somebody's going to tell you, or you can use tonnage times 3, but now you know why. Now, let's say you have an absorption chiller. So that's actually tonnage times 4 based on its flow rate, and you can have all that equation if you want to look that up. The Google is great for that. And you might be saying, Trace, this all started out with the equation 0.001 times recirculation rate, which was the tonnage times 3, times the delta T, times our factor. But you know what? I don't need to know any of this because I use a different equation. And the equation you might use is evaporation equals 1.8 gallons per ton. So there might be a couple people out there that say they use that. Well, because I'm a nice guy, I'm going to prove that one for you. So if you take 15,000 BTUs, which is how many BTUs a tower is supposed to remove, times our 1 pound divided by 1,000 BTUs, remember it takes 1,000 BTUs to evaporate a pound of water, and then you multiply that by 1 gallon, and how much does a water weigh? It weighs 8.345 pounds, so you multiply that by 1 gallon divided by 8.345. If you do all that work, you're going to get 1.8. So you're doing the same thing, you just didn't realize where it came from. Now, the issue with that is that assumes 100% evaporation. It doesn't take into account our factor that we talked about before, and it also assumes a constant delta T. So again, when you understand the equations that you are using, you understand the inputs that it's asking for, and now you're able to put better data in and get better data out. So I sure hope that you've enjoyed me attempting to do math on the podcast. Again, you all asked for it. I didn't want to give it to you. But since I've given it to you, many of you have written in and said that you have enjoyed it. So I'm hoping this helps. And I hope you keep coming up with ideas, different equations that you want me to prove. This equation right here came from a Scaling Up Nation member. They asked me, what is this tonnage times 3 about? So went ahead and did it on the show. So folks, what do you want to know about? What are the equations that you have questions on? What water treatment issues do you want to talk about so we can make sure the show is doing exactly what you need it to do? Well, folks, next week we have got a show on sales. And I've been to a seminar from this gentleman. His name is Brian Gray, and he just does a great job of helping us learn how to present better when it comes to not only gathering, but delivering our proposals. And I know you're going to join that. In the meantime, I hope you have a great week. I hope you choose to do something significant to increase your base of water treatment colleagues so you now can bounce ideas off of. So whatever you need to do that, please think about doing that, and I will talk with you next week on Scaling Up H2O. Nation, one of the keys of my success has been being a member of groups of people that help me get to the next level. Let's face it, when we are bombarded with the day-to-day of all of these tasks that we have to do in our job, it is so easy for us not to work on the things that we decided were most important to us. We work on things that are most important to other people. The Rising Tide Mastermind is a group that will make sure that you're considering all of the items that are available to you and making sure that you are getting to the next level. Simply put, you will get where you want to go faster when you have a group of people that are encouraging you and keeping you accountable to get there. Go to scalinguph2o.com/mastermind to see if this is the right group for you.